So in this problem we have a wire with a current I, and down here there's a square loop, a distance h away from the wire with these dimensions, and this wire produces a magnetic field going into the board everywhere inside the loop. So the flux through the loop is given by this, and the magnetic field that the wire produces is equal to this. It depends on the distance r away from the wire. And let's look at a little bit of area here in this loop. This little bit of area is L times dr. So we write that for dA. And so the flux is just the integral of this from r equals h to h plus w. So the flux going through the square loop is given by this. Once we do the integral, we just get this natural log. So we know the flux going through the square loop. So now the next thing we know is that the EMF induced in the square loop is the change in the flux with respect to time. And everything in the equation for the flux is constant except the current. So the current is changing with respect to time. And we know how this current changes with respect to time because we know the current is this, so the derivative of the current is B. So we plug that into di dt. And so the EMF induced in the square loop is given by this equation where we replace di dt by B. So now that we know the EMF induced in the square wire, we can see that it's equal to this number. We just plug in what mu naught is, what L is, and H and B and so forth, and we can calculate the numerical value of this. So if we multiply this out, we get this 4.8 times 10 to the minus 6 volts. So that's the EMF that's induced in the square wire. So let's look at what's happening. Current is going this way, EMF is induced in this wire. The magnetic field increases in here, so a current is induced in this direction to oppose the change in flux.